All right, so our goal for this derivation is to determine the electric field at point P due to this line of charge. Now, in this case, we're going to assume that point P is located at the midpoint of a bisector, so that I could define this to be the center point of the line. So this is going to be x equals 0 here. And we're going to end up with the left side, therefore being in a position of x equals negative L over 2. And the right side being a position of x equals positive L over 2. So that's how we're going to set up this problem. There are different ways to do this. For example, I could have defined the left side of the rod to be x equals 0 and the right side would be x equals L. Often the coordinate system will be defined for you. If it's not, then it doesn't matter which coordinate system you use, as long as your work matches whatever you have defined. So the first thing you want to do is, if they don't give you a coordinate system or a picture or anything like that, is you need to set up your coordinate system. And you need to make sure that you're always being consistent with your coordinate system. So one thing you have to do is you have to start with a picture. So if no picture is provided for you, make sure you draw a picture. Now sometimes on AP questions, they will tell you to draw a picture and maybe establish your coordinate system or draw the electric field vector or something along those lines. But you need to make sure that if they don't specifically tell you to do that, that you need to do it yourself, because you're defining the coordinate system at that point. So we are going to assume, for our purposes here, that positive Q, our line of charge is positive. This process would be similar if this was a negatively charged, except for instead of having the electric field point away from a positive, if our charged rod was negative, the electric field would point towards it, but the process would be exactly the same. So the next thing you want to do is you want to choose a representative piece of the rod at which to use as your infinitesimally small charge. Now when you pick that infinitesimally small charge to use as an example, that you don't choose an end point or like a midpoint. You don't want to choose something with perfect symmetry. So for example, I wouldn't ever want to use the left end or the right end, and I would not want to choose a point dead in the middle. So I'm going to choose a little point here. So I'm going to draw in my slice. So this is the next thing you have to do, is you need to actually draw in your infinitesimally small slice. Now I'm also going to give it some information. Like I'm going to define this as having a charge dq. I'm going to define it as having a width of dx. Now I'm using dx in this case because I've defined this as x. If, for example, my rod was aligned vertically, and I define my x-axis to be that direction and my y-axis to be this direction, then my slices here might be dy's. So you have to be careful with your coordinates. So I'm defining this as a little bit of dx. dr would not be appropriate in this case because r is going to be a separate dimension. It's going to be the dimension between my infinitesimally small charge and point P. So I can actually draw that in here. So my dr is going to be here. Well, not dr, it's actually just going to be r. So r is a vector, and it is a vector. It's a vector that starts at your point and goes towards point P. So my r hat direction is actually there. We're not going to use the r hat direction because we're going to look at x and y's, but it would technically be there. So that's going to be r. Now one thing I am assuming is I am assuming that this rod is thin. I didn't write out all of the problems here, but what's really nice about this thin is basically I don't need to worry about a thickness because the thickness is negligible. So that way I don't have to worry about any sort of vertical weirdness because of the rod. I can just assume that that is actually a point charge dq. So even though I'm drawing it like a little rectangle, it's actually an infinitesimally small point because dx is infinitesimally small, and just by definition of it being a thin rod, dy is negligible. So there's like almost no y component to this thing at all. So this is a point charge. Okay, and point P is located at a distance r away from this point on the rod. So then I need to figure out where would the electric field point. Well, my electric field would be a vector that points away. So in this case, it would be here. So I'm going to have an infinitesimally small, so dE is going to be my infinitesimally small electric field due to dQ that's at point P. So the electric field is for point P, so it starts on point P, and then because this is a positive rod, it points away, radially away, so it is along the same radius dr. I didn't quite get that perfectly parallel to R, but it's close enough. So that's my setup. So essentially what I've done is I've set this up, and then I can define what dE is because dQ is a point charge. So I can define that dE has a magnitude of K dQ over R squared, because any point charge has an electric field of E is equal to KQ over R squared, where Q is your source. And I'm essentially looking at the electric field due to charge Q. Well, Q has a charge of dQ, and the electric field is dE. So that's the substitution that I'm making. So that's where this equation comes from, because we're treating that as the point charge. Now, that's the magnitude. The problem here in this case is that the electric field is a vector. And I actually have two components to this vector. I have an x component and I have a y component. So I'm going to have a dEx and I'm going to have a dEy. I'm going to move this dE over here so it's not in my way. And dEx and dEy are related by some angle theta. And that angle theta is going to be the same as the angle here that's essentially made with my rod. So we're going to see that this angle comes into play in multiple cases. Now, if I had chosen a different point, then a lot of things would change. My R would be different, my strength, my magnitude of my electric field would be different, the angle that they make would be different. So I have a lot of different variables. So what I'm going to want to do is break this up into components. So I'm going to define dEx and I'm going to define dEy. And I have to treat them separately, just like you would do any two-dimensional problem. So in the x direction, dEx is going to be K dQ over R squared. And then dEx in this case is going to be the adjacent side, so it's going to be cosine theta. And dEy is going to be K dQ over R squared sine theta. Now, this looks like I might have a whole lot of work to do. But if we look at this rod, because point P is in the center, if I were to look at this point dQ and I was to look at the exact same point, the exact same distance x, so this is actually, that's another dimension here. This little charge here is at some position x. If I were to look at some point over here on the exact same distance x, just on the opposite side, its electric field would be pointing the opposite way. And what you'd find is the x components due to this rod are all going to cancel out. But all of the y components are going to point in the positive y direction. None of them are going to point in the negative y direction. So actually, if I were to integrate dEx, this is actually going to give me an electric field that equals 0. So I can just say that, hey, because of symmetry, Ex is equal to 0. So I don't need to go through and solve. Now, you could do the setup and you could solve it and you could prove that it adds up to 0. And I've seen that as a problem, to prove that it's 0. In that case, you'd have to do everything we're about to do for y in terms of the x component over here. But once you can do it for one component, it's not too hard to do it for the other. You're just changing up your definition of your trig function. So we've now looked at Ex, that's going to be 0, so let's come over and look at the y. So I'm going to want to integrate across this rod. Now, I'm going to want to integrate across the rod, so I'm going to want to integrate from the left side of my rod to the right side of my rod. I'm going to assume that when I'm over here at the left, that Ey is 0, and that by the time I've made it all the way over here, my Ey is going to be equal to my total value. So my EY is going to be my total electric field. So even though my Y direction is up, I'm going to integrate across the X direction. So what I need to do is I need to get all of these variables into terms of X. I need all of my variables to be in terms of X because I'm going to integrate in the X direction. So that's going to be the big effort. So we need to take a look at every single one of these variables. Now, we are also going to assume that our rod here is uniform. So if we're assuming that our rod is uniform, then what we can assume is that if we have a uniform rod, that our linear mass density is going to equal the total charge over the length L. And we're defining positive Q and L to be known values. But I'm also going to know that for dq and dx, that because this is uniform, no matter which little tiny infinitesimally small slice I pick, dq over dx is always going to equal the same thing as q over L. So that's because this is uniform. If it's not uniform, then dq over dx will still equal lambda, and they can give me a function for lambda in terms of x, but the q over L won't be true. So if it's not uniform, you cannot use the q over L, because every little section might have a different value. But in this case, this is true. So what this will allow me to do is if I solve for dq is going to be q over L times dx. Q and L are constants. They're constants that would be allowed in my final answer if I was to have a list of variables. So what I'm doing here is I can sub in for dq and I can get this in terms of dx. So I can write that dEy is equal to k q over L dx. All right, so we've done that first part. We also need to take a look at sine theta. Theta is not going to be an allowed variable, and theta is not a constant because my angle is going to change depending on which slice I pick. So if I look here, one thing they would have told me is they would have told me the location of P. So I'm going to define P as being at a vertical position Y. So I'm going to define this Y as a constant. So if I were to look at theta, theta has some relationships in this triangle here with dx and dex and dey, but it also relates down here. So that if I wanted to define sine of theta is going to be opposite over hypotenuse. Well, the opposite side is going to be y. The hypotenuse is going to be r. So sine theta is going to equal y over r. Y is going to be an allowed constant. It's going to be something that's defined. So I could sub in for sine theta and get y over r. So sine theta is going to be y over r. And then that's all going to be over r squared. So at this point in time, what I can do is I can actually pull this r down here, and I can get dEy is going to equal k q y over L dx all over r cubed. So I've subbed in for the sine theta y over r, and now I have an r cubed here. This whole bit right here, this is all constant. So all of those variables in that case are allowed. dx is in terms of x, so now I need to find a way to get rid of r. R is a problem. Well, I'll still have this triangle here. So what I can do is I can use the Pythagorean theorem and say, well, r squared is going to equal x squared plus y squared. X is a variable, y is a constant. So r is going to essentially be x squared plus y squared square rooted, but I'm going to put that up to the 1/2 because when I substitute in, I'm going to need r cubed. R cubed is going to be x squared plus y squared to the 3/2. So then you can take this and substitute in over here, and I get dEy is equal to k q y over L as constants. I'm going to get r cubed on the bottom. So I'm going to end up with dx over x squared plus y squared to the 3/2. And this can now be integrated. So this is a differential equation that can be solved for the electric field. So this is all the setup part. So this is basically your goal to get before you go to integrate, because K is a constant, Q is a constant, Y is a constant, L is a constant, Y is a constant. So basically the only variable I have over here is X. So that's kind of like the first big part of that, is to get to that point. So then the next part is actually going through and integrating. Alright, so let's assume now that we have the dEy is equal to kqy over L, dx over x squared plus y squared to the 3/2. This is ready to integrate. So I'm going to integrate, and essentially I'm going to start over here at the left side of my rod. At the left side of my rod, I'm in a position of x equals 0, and I'm going to, or actually I'm not at x equals 0. I am at x equals negative L over 2. And then I'm going to integrate over here to L over 2. Now, for example, if they didn't define x equals 0 here, you could have defined this as x equals 0 and x equals L, and I could go through and integrate. Additionally, some of you who have gone further in calculus know that this is going to be symmetrical, so negative L over 2 to 0 is going to be the same integral value as 0 to L over 2, so you might go, oh, well, I'm going to just do 2 of 0 to L over 2. That's okay as long as you've properly defined it according to the physical system. That's the difference between math and physics, is you have to make sure that your equations and your limits match the physical system. So if you're going to make a calculus simplification to make it easier, you can do that. That's perfectly acceptable. But you need to make sure you start with your limits physically matching your dimensions. And then for dEy, that's going to integrate from 0 to E, or I could do EY actually. It's better to stick with EY, because if this was not symmetrical, you would still have an EX and an EY. In this case, EY is going to equal Z because EX is equal to 0. So that way we can go through and fix that in the end. So EY will equal E at the end, but we're good until then. So this left side's pretty easy to integrate, because if you integrate dEy, you're just going to get EY, and you're going to evaluate it between 0 and EY. Over here on this side, the K, the Q, the Y, and the L can get pulled out in front, and then you're going to have this integral of negative L over 2 to L over 2 of dx over x squared plus y squared to the 3/2. Now, those of you that are a little better at calculus will notice that this is a very complicated integral. And actually, a u substitution is not going to work in this case because there's no x in the numerator. So this is actually a special integral. There are other ways you could solve this. I think you could do this using a trig substitution and so forth. But in this case, we're just going to use a standard integral, because this is actually a standard integral. So if you were to look this integral up on an integral table, it would be there for you. On the AP exam, a lot of times they'll just ask you to set up but not solve. And the reason they do that is because the integration here is not standard. And they don't want to just give you some huge table of integrals from which to work with. So this is a standard integral. And I would memorize it just because you're going to use it a lot in the derivation packet. So it's handy to have. But like I said, if this was an actual AP question, they don't expect you to have this memorized. So if they want you to use it, they have to give it to you. But on a multiple choice question, they could give you a whole bunch of answers. And if you know what the answer to the integral was, that would give you a way to kind of eliminate some of the answer choices that don't make sense. So, because they might ask, because you can always use things like limits and stuff like that to check answers as well. So A in this case is going to be a constant. In our case, y is a constant. So when we substitute in this case, we have to make, this is going to be x. But we have to be careful because if they had rotated this 90 degrees, x can be any variable. So x could have been a y or x could have been a z. But in all cases, a is a constant. So it's whatever constant you have. In this case, y is our constant. So what this tells me is that over here, that I'm going to get ey minus 0 is equal to kqy over L. And then the answer to this integral is x over a, but in this case a is y squared square root of x squared plus y squared. And we're going to evaluate that from negative L over 2 to L over 2. If we take a look, I can actually move that y squared out over here. So if I were to do that, I'd move that over here. And then you notice that actually one of the y's cancels out. So I would get ey is equal to kq over L times y. And then I'm going to end up with x being L over 2 over L over 2 squared plus y squared. Square rooted. So I got the square root there on the bottom. And then I'm going to have to subtract x being a negative L over 2 over the square root of negative L over 2 squared plus y squared. So if we take a look, we have here, we have this negative and a negative. So that negative and negative is actually going to become positive. Because this negative here is inside of the square, you're going to end up with the same L over 2 squared here. So the denominator in this case is going to be the same. So we're going to have L over 2 plus L over 2. So that's going to give us that ey is equal to kq over Ly times L over the square root of L squared over 4 plus y squared. And then actually L cancels out here. So our final answer ends up being ey, which is equal to E in this case, is going to be kq over y times the square root of 1 over 4 L squared plus y squared. And that would be our final answer. So, and then if you wanted to define this in terms of a vector, I could define E as being, and this could be in the, not the y hat, sorry. Could do this in the j hat direction. So if I wanted to define this in unit vectors, or I could define it as up the page if I wanted to make this a vector. So you can see that the larger the charge, the stronger the electric field. But if you were to end up pulling this y inside, you do end up with a larger y being a smaller electric field, but it's not like something simple like half or anything along those lines. But your electric field will decrease in magnitude the further away that you get. So there you go. That's how you do the derivation for something like a line of charge that is not a point charge. But we are assuming that we're treating this one as a point charge. And some of the variations that you're going to do is like point P could be anywhere. So it could be off to the side. It could be over the side over here. Lots of variations just of a line of charge. This was a uniform rod. You're going to look at cases that you have a non-uniform rod. You're going to look at cases where your line is actually a curve. So you're going to look at kind of like, You could do like a ring of charge. So you could have a ring and you could have a point here or a point here, or you could have like a semicircle of charge and you could have some sort of point. And then once again, we're going to use a ring of charge to actually determine like a sheet of charge. So we're going to actually sum up a whole bunch of rings and to actually make a sheet instead of just a point charge. So lots of different variations to have. Good luck.